Today I'd like to do one more example for constructing a confidence interval, and this example is in your textbook. A manufacturer of pharmaceutical products has analyzed a specimen from each batch of a product to verify the concentration of an active ingredient. The measurement process, the chemical analysis, is not exactly precise, but repeated measurements on the same specimen will give different results. The results of repeated measurements tend to follow a normal distribution quite closely. The analysis procedure has no bias, so the mean mu of the population of all the measurements is the true concentration in the specimen. So if we repeatedly measure the same thing, we'll get slightly different answers, but the mean of that sampling distribution will be the true mean of the population. The standard deviation of the distribution is 0.0068. The three analyses gave these following concentrations: 0.8403, 0.8363, and 0.8447. You recall from yesterday, the formula for a confidence interval is x bar, the estimate, plus or minus a critical value, which we called z star, times the standard error of the estimate, sigma over square root of n. First of all, for this problem, we need to find out x bar. Well, since you know the three observations, simply put them in your calculator, add them up, and divide by 3. Do that on your own while I do it on the overhead. Next, we need to figure out z star. Well, if you remember, z star is the magic z value that gives you the confidence level that you want. For this problem, the book would like a 99% confidence interval. We abbreviate that with a capital letter C for the confidence level being 99%. Let's look at another page for just a second. If I want the confidence level to be 99%, it means this area in here is 99%. Like yesterday we did 95%. If that area is 99%, then the rest of this here, and this here must be the other 1%. Half of it is down here, and half of it is over here. So that all three of those things add up to give me 1. If you use your pink chart, you're now going to look up this number on the inside of the pink chart. Grab your pink chart, look at that. You notice that the number falls between negative 2.57, which went with 0.0051, and negative 2.58, which went with which was 0.0049. At this point, it doesn't matter which one you pick. I'm going to use this one. If there's a closer one, you'll go with that. If you're someone who uses your calculator, you could do inverse norm 0.005. That inverse norm is under the distributions menu. And when you do inverse norm 0.005, you get negative 2.575829303, which rounds off to the value that we've chosen. When you use a z star, you're only concerned with a positive z star. So this z star value right now is going to be 2.58. Then I'll use the given information to fill in the rest of the equation. So again, my equation is x bar plus or minus z star times sigma over the square root of n. X bar for this problem was 0.8404 plus or minus the z star we just said was 2.58, and the rest of the given information, sigma is 0.0068, and we had a sample of 3 specimens. Working this out, you get 0.8404 plus or minus 0.0101, and that gives me 0.8303 to 0.8505. At this point, you need to remember to write a conclusion, conclusion being one of the critical parts of your problem. In this case, you write, I am 99% confident the true mean, oh yeah, what's the true mean? It's the true concentration of the specimen is between those two numbers. What are those two numbers? 0.8303 and 0.8505. And literally, sometimes I will write, just as I did, the true mean, mark it out, write what the mean represents, is between, and then fill in your numbers to remind you that that's the ideal we want. It's not there's a 99% chance the mean is either in there or it's not, but we're pretty sure because of the method that we did that the true mean will lie in that interval.